तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
As we were discussing about anaerobic treatment, we have seen what is the difference between anaerobic treatment and aerobic treatment, and what are the different biochemical pathways involved in the anaerobic degradation, and we have also seen what are the conducive environmental conditions for the better performance of anaerobic processes, and we have seen the different types of bacteria involved in the process and what is the role of each bacteria and what is the nature of each bacteria. Today we will discuss about what are the conventional and modified reactors available which is using anaerobic technology for the treatment of wastewater. So, coming to the conventional anaerobic treatment systems or classical anaerobic treatment system, the septic tank was there from 19th century itself. It was invented by Cameron in England. He was the first person who has used this septic tank. Septic tank is nothing but a tank which allow the settlement of suspended solids in wastewater, and the settling time is so large, that means it gives a time of 5 to 10 days. So, during this period whatever is the suspended solids present in the wastewater will be settling down and the tank will not be having any oxygen supply. So, what will happen? The sludge which is settled in the bottom of the tank will be under anaerobic conditions. At these conditions anaerobic bacteria will prevail and the solids will be undergoing anaerobic degradation. So, as a result what will happen? The organic matter present in the system will be getting reduced and biogas will be produced. The biogas will be coming from the bottom of the system to the top. So, because of this biomass movement some of the solids may be getting floated. This is a disadvantage of the septic tank. I will show the picture of the septic tank. So, this is the one. So, this is a reactor or any closed container and it is not open to the atmosphere, only one vent pipe is there and influent is coming like this, and enough detention time is provided so that all the organic matter in the suspended form will be settling down and you will be getting a sludge layer here. The sludge layer will be having so much of organic matter and the oxygen availability is almost nil. So, entire system will be under anaerobic condition. So, as a result what will happen? This sludge undergoes anaerobic decomposition and biogas will be produced as byproduct. This biogas will be coming in this direction, in the upward direction, and settling will be taking place in the downward direction. Due to this biogas movement there will be some turbulence. So, as a result some particles whatever is already settled may come up and it will float in the surface of the septic tank. That is one of the disadvantages of this septic tank. And whatever the scum and oil present in the influent, that will be definitely coming up to the bottom of the tank. So, usually in a septic tank there will be a scum board which prevents the scum to enter in the effluent channel. So, the scum will be retained here and whatever is the treated effluent it will be coming out through this one. So, what is happening in system? The organic content of the wastewater will be decreasing drastically because influent will be having lot of suspended solids and all the suspended solids will be getting removed from the system and the effluent will be having only the soluble COD whatever is coming out along with the effluent, and a part of the soluble COD also will be getting removed in the septic tank. So, this was the conventional anaerobic system which was used in 19th century, in the first anaerobic reactor which was being used in the world. And imofcorn, this is another anaerobic unit which is conventionally used. This is a modification of septic tank because I have already told in septic tank because of the biogas movement, the solids can float. So in IMF con or IMF tank it is impossible, because here we can see that here this arrangement separates the digestion zone and settling zone, and gas or the biogas produced due to the anaerobic digestion is not coming or not entering in the settling zone. The biogas will be stored this portion only, in the digestion zone only. So there will not be any turbulence created in the system. So what will happen? You will be getting relatively clear effluent in the IMF tank, and this is the vein through which the biogas is removed from the system, and all the digestion will be taking place here, and this is the sludge layer, and this portion, entire portion will be acting as the settling zone, and the effluent will be collected from here. So you will be getting much more clarified effluent from the IMF tank compared to septic tank. And if you see the history, we can see that the first biggest public health system or environmental or wastewater treatment system employed was in Chicago in 1935. There they have used this IMF tank in series. The treatment capacity of the system was 1.8 million liters per day. So the first treatment system in the history of environmental engineering was made up of this IMF cons, then or IMF tanks. So what is the problem? Why this anaerobic technology is not coming into existence, or it is not becoming popular even now? Okay, we will see the reason in detail after a while. Okay, another conventional anaerobic system is the anaerobic lagoons, that we have discussed in detail when we were discussing about ponds and lagoons. So in anaerobic lagoons, what is happening is we can go for high organic loading, and the waste will be staying there for a long time. So what will happen? Because of the high organic loading rate, whatever the air entering or whatever is the oxygen entering from the atmosphere will not be enough for maintaining an aerobic condition in the system. So entire pond will be in anaerobic condition. So what will happen? Because of the anaerobic bacteria, degradation will be taking place, and a portion of the COD will be getting removed from the system. So if you talk about the efficiency of this anaerobic pond, if you give sufficiently long detention time, say 10 days, 5 to 10 days, then you will be getting an efficiency of 50 to 70%, or we can find out the efficiency using this empirical formula 1 minus 2.5 by HRT raised to 0.50. Here HRT is the hydraulic retention time in days. So this is the expression derived from many field experience, or they have studied many field anaerobic ponds and they have evaluated the performance, and from that performance they reached this empirical equation. So we can see that the HRT is in the range of 5 to 10 days. So the volume of the reactor required will be very high. So that is one of the reasons why anaerobic process did not become popular for domestic wastewater treatment, because though anaerobic treatment was the first one come into existence in 1935 as a treatment process, but afterwards aerobic system took over anaerobic process, because aerobic system we can achieve very high efficiency, say 90 to 95% within few hours. Usually we give 8 to 10 hours HRT in the aeration tank. So compared to this one, anaerobic system requires lot more time. So naturally the volume of the treatment system will be very high. So if we can reduce the detention time, definitely the treatment system will become more attractive. The reason is we have seen that anaerobic process is having many advantages over aerobic process. If you are, the energy requirement is very less, because in aerobic system we have to aerate the wastewater, we have to supply oxygen externally to meet the oxygen requirement, but in anaerobic process oxygen is not required at all, because the substrate will be acting as the electron donor as well as electron acceptor. The another reason is the sludge production. Anaerobic process, we have seen that the organic matter whatever is used for the anabolic purpose or for anabolism or for cell synthesis is very less than 10%, whereas in aerobic process it is around 40 to 60%. So definitely the sludge produced in anaerobic process is much less compared to aerobic process. So sludge handling is not a problem at all, and Moreover, the sludge whatever is generated in anaerobic process is almost mineralized. So, we do not have to go for any further treatment, we can directly put it into sludge drying beds. So, anaerobic process is having many advantages over aerobic process, but the most important disadvantage is this one, it takes large detention time to get high efficiency. So, if we can overcome this one, anaerobic process will definitely become popular. So, to avoid that one or to make anaerobic process popular, okay, people were working in this area for long time, so they have come up with this high rate processes. In high rate processes, what is happening is the system is able to retain high concentrations of active biomass. Okay, that means the microbial concentration in the system will be very high. Okay, we have seen that the regeneration time or the reproduction time of this anaerobic bacteria, especially the methanogens, the methane producing bacteria is very high. If the regeneration time or reproduction time is very high, naturally the biomass concentration will be very less. So, if you are allowing the biomass whatever is generated in the system to go out, what will happen? The system will not be having enough biomass. So, naturally the treatment efficiency will be coming down. So, if we can clearly divide the hydraulic retention time and biological sludge retention time, then the system can hold lot of biomass inside. So, once the biomass concentration inside the system is very high, naturally the treatment efficiency will be high, because in any biological system, as I have already told many times, the workers are microorganisms. So, if you can increase the number of workers, definitely the treatment efficiency will be more. So, that is the very principle of this high rate processes. So, now we will see what are the mechanism of sludge retention in high rate anaerobic systems. So, the sludge can be retained basically in two different ways. One is the systems based on immobilization of the sludge, and another one is systems based on liquid solid separation with the return of the separated solids to the reactor. So, when we talk about the systems based on immobilization of sludge, the reactors which are working under this principle are upflow and downflow anaerobic filter, sludge bed reactors such as granular bed expanded or fluidized reactors. So, in these cases what is happening, some inert material is there, either it is sand or plastic media or any synthetic media, on that the biomass will be growing. So, naturally the medium will be having high density, so it will not be going out of the system along with the liquid. So, whatever the biomass generated in the system will be staying inside the system. So, definitely we will be increasing the biomass concentration. And in the second system what we are doing is, this is a form of modified activated sludge process. So, in activated sludge process what we are doing, in the aeration tank we have lot of microorganisms. So, we are allowing the microorganism to settle in the secondary sedimentation tank, and we want to maintain a high concentration of biomass in the aeration tank. So, what we do, the settled biomass whatever is there in the secondary sedimentation tank, we allow a portion of that one to come to the aeration tank. So, naturally the biomass concentration in the aeration tank increase. So, the similar system works in anaerobic process also. So, there we provide some arrangement which can easily separate the solid and liquid from the effluent, and the solid will be coming back to the system. So, this arrangement can be provided either within the system or as a separate unit. So, depending upon that one we can see different types of reactors. So, we will see the reactors whatever is commonly used, or the reactors which is working on this high rate principle, we will discuss in detail. So, these are the anaerobic filters. So, this one is upflow anaerobic filter and this one is downflow anaerobic filter. So, here what is happening is, here we can see this dashed lines, this is the filter media. This can be any inert material on which microorganisms can grow fast. So, the influent will be going like this, and active biomass will be growing in this filter media, just like our trickling filter or rotating biological contactors. The biomass will be growing in this filter media. Only thing, the entire system is in anaerobic condition because nothing is open to the atmosphere. So no entry of air will be there in the system. So influent will be going like this, and the organic matter whatever is present in the influent will be coming in contact with the biomass in the filter, and the biomass will be utilizing the organic matter, and some more new cells will be generated, and the remaining part will be converted to carbon dioxide and methane, and the biogas is collected here. This system, these anaerobic filters are commonly used in industrial wastewater treatment where the organic loading is very high. Okay. This system can take lot of organic loading in the range of 10 to 20 kilogram per meter cube, that is the organic loading rate. And one of the problems which is usually faced in this type of filters is clogging, because with respect to time what will happen, the biomass concentration or biomass thickness in the filter will be very high, and that will be slowly decreasing the porosity of the medium, and filter clogging can take place. And the reason for the clogging is this influent will be having lot of suspended solids. So that suspended solids will be coming and sitting here in the bottom portion of the filter. So that can also clog the filter. So what will happen afterwards? There may not be sufficient flow and lot of head loss will be there, etc. And sometimes if the influent flow rate is not sufficient, what usually is done is recirculate a portion of the effluent, treated effluent here, so that it will get enough velocity for the flow. So this is anaerobic filter. And now coming to the downflow fixed bed anaerobic filter. Here the influent is coming from the top of the filter and effluent is collected from the bottom of the filter, and here we can have the biogas collection system, and this is the filter media and on which the biomass will be growing. The advantage of this system is the influent is coming like this and biodegradation is taking place. As a result, the biogas methane and carbon dioxide will be produced. The gas will be going in the upward direction and the influent will be coming in the downward direction. So because of that one, a proper contact between the wastewater and the microbial system will be taking place, because lot of turbulence will be created in the system. So short circuiting, clogging, etc. can be minimized if you go for a downflow fixed bed anaerobic filter. So these two are examples of high rate anaerobic reactors. Now we will see another type of high rate reactor. So this is the example of a fluidized bed reactor. So here what happens, we use sand, coal or any plastic media on which the microorganisms can grow as the supporting material. So in the reactor we will be putting the supporting material, and with respect to time what will happen, the microorganism whatever is present in the system will be getting attached to the inert material or the support material whatever we have provided here. The support material will be having high concentration of microorganism, and the influent will be coming from the upward direction. So from here it will be entering and it will be going in this direction, and the influent flow velocity will be very high, so that the medium will be in the fluidized form. That means one particle will not be in contact with the other particle, everything will be in a fluidized form. So as a result of this fluidization, what happens, there will be very good contact between the microorganism as well as the organic matter whatever is present in the wastewater. So the treatment efficiency will be very high, and whatever the biogas produced, it will be going from here and we can collect the treated effluent from here. Because the microbial growth is in the form of attached, microbial growth is attached one here, the effluent will be relatively clear because not much microorganisms will be coming out along with the effluent. And in this system the recirculation of effluent is most of the time a must. The reason is influent may not be having enough velocity to fluidize the bed depending upon the bed material, because if it is sand particles, you know the specific gravity is very high. So we need a very high upflow velocity to fluidize the material. Most of the time we recirculate the treated effluent to give the enough upward velocity here. And now coming to the expanded bed reactor, this is an example of expanded bed reactor. here all the particles will not be in the expanded form, all the particles will not be in the fluidized form. Okay, here the velocity, the or the upward velocity will be relatively low compared to the fluidized system. So the bed will be expanding up to 30% of the initial height. Say initial height was only up to here, after the influent passage it will be expanding up to here. So how can we distinguish the fluidized reactor and an expanded bed reactor? There is no clear cut distinction between these two, but if you see the expansion, if the expansion is less than 30% of the original bed height, then we call it as an expanded bed reactor, and if the expansion is more than 30%, we call it as a fluidized bed reactor. The advantage of expanded bed reactor compared to the fluidized bed reactor is here the recirculation is less compared to the expanded fluidized bed reactor, because here we want to expand it only 30%, so the velocity will be less compared to this reactor. So the pumping cost can be reduced in expanded bed reactor compared to fluidized bed reactor, but efficiency wise expanded bed reactor efficiency will be lower than fluidized bed reactor, because here you will be getting more contact with the biomass and the organic matter in the wastewater. Now we will see another type of system. So the one whatever we have discussed so far, the anaerobic filters and fluidized and expanded bed reactors are working on immobilized reactor systems. That means some inert material we are providing, on that the microorganisms are getting attached. So these two reactors whatever we have seen now, the anaerobic filter, downflow fixed bed anaerobic reactor, expanded bed reactor and fluidized bed reactor, all these four are coming under immobilized reactors, because the bacteria are growing on some support medium. The support medium can be some natural material or synthetic material. If you use synthetic material, especially the plastic and like substances, what will happen? The specific gravity of the substance is, specific gravity of the particle is low, so the velocity required to fluidize them or expand the bed will be less, so pumping cost can be reduced drastically. Now we will come to the systems which use the solid liquid separation process, and after that one the sludge will be recycling to the system. So that way we can increase the biomass concentration in the system. So this is the example of an anaerobic contact process. So this is the anaerobic chamber, the influent is coming here, and digestion, this is the digestion zone. So anaerobic reactions will be taking place, as a result the biogas will be produced and we will be getting the effluent through this one. Because of this biogas production, what will happen? Entire reactor will be getting mixed up thoroughly. If the mixing is not proper, we can provide the mixing externally also. So definitely whatever the biomass concentration inside the system, same concentration will be coming out along with the effluent. So here we are collecting the effluent and allow it to settle. So this is a settler or a sedimentation tank. So here all the biomass whatever is coming along with the effluent will be getting settled, and all the biomass will be recycled to the system along with the influent. So we can see here. So what will happen? The biomass concentration in the system will be very high. So we can reduce the hydraulic retention time considerably. So this is known as anaerobic contact process. Here the anaerobic digestion and the settler or the sedimentation tank are separate units. So the modified form of this anaerobic contact process is the UASB reactor. So this is the schematic of a UASB reactor. Here what is happening? The influent is coming here. We will be having anaerobic bacteria here, and the effluent will be going upward and we will be collecting from here. But in the reactor itself, some provisions are provided. So the reactor itself, a portion of the reactor itself will be acting as a settling zone or a sedimentation zone. So with respect to time, the biomass concentration in the reactor will be very high. So we can have a very high efficiency, or we will get a high treatment efficiency within a short contact period. So what happens here? See, we can see some projections here or deflecting beams here, and we have some arrangement here also. So the treated water will be coming here, and afterwards we can see that this portion is getting expanded. So this portion will be acting as a settling chamber or a sedimentation tank, and this portion will be acting as a reactor or digestion zone. Okay, this is a modified form of immerse tanks, whatever we have seen initially, and the treated effluent will be collected from here and biogas will be collected from here. So here we are not providing any external unit for the biomass settling, but the system itself will be providing the settlement of the biomass, or the system will not allow any biomass to escape along with the effluent. So this is another type of reactor. So there is no separate GLSS, that means gas liquid solid separator. So this is the plastic cover. So influent is coming, sludge blanket is here. Okay, the velocity is adjusted in such a way that by the time the water reaches here or the treated water reaches here, all the biomass whatever is present in the system will be coming back to the sludge blanket. So by this way the biomass concentration in the system will be increased. And this is another modification. Here instead of flocculent sludge we use granular sludge. So what we can do is, since the sludge is in the granular form, the settling velocity will be very high. So we can use or we can treat a high organic waste, or we can reduce the detention time considerably in such reactors. This is known as an EGSB reactor, that means expanded granular sludge bed reactor. So all these reactors are coming under high rate reactors. Now we will see the efficiencies of each reactor in detail. So as I have already explained, the anaerobic filter we can go for very high organic loading, that means in the range of 10 to 20 kilograms COD per meter cube per day, and it is mostly used for high strength industrial wastewater treatment. And the efficiency, okay, we can derive the equation for efficiency using kinetics approach, but there are empirical expressions available if you want to find out the efficiency of the system. The efficiency of this anaerobic filter can be found out using this empirical formula. E is equal to 1 minus 0.87 HRT raised to minus 0.50. Here HRT should be in hours. We have seen in anaerobic lagoons the efficiency is given by an empirical formula where the HRT was given as in days, but in anaerobic filter this HRT is given in terms of hours. Now coming to the expanded or fluidized reactor, I have already mentioned that the attachment media is usually sand, anthracite and plastic, and usually anthracite and plastic are preferred nowadays. The reason is the pumping cost can be reduced considerably. And if you want to find out the efficiency of an expanded bed or a fluidized bed reactor, we can use this empirical formula. E is equal to 1 minus 0.56 HRT raised to minus 0.60. And as we have seen, upflow anaerobic sludge blanket reactor, and it was developed by Lettinga in 1970s, and this is the most commonly used high rate reactor for municipal wastewater treatment. Even in India we have many USP plants at present which is used for the treatment of domestic wastewater and domestic and industrial wastewater together. For example, in Kanpur, initially they have set up a 5 MLD treatment plant for the treatment of domestic wastewater, and by seeing that it is a success, they have put up another treatment plant which is having a capacity of 36 MLD, which is using domestic sewage as well as the wastewater from the tannery industries. So this is used for the treatment of municipal as well as industrial wastewaters. So this is the example of an upflow anaerobic sludge blanket reactor, because this is the one which is most commonly used. We will see in detail what is happening in a UASB reactor. So in UASB reactor, the influent will be coming from the bottom of the reactor, and we can see that this is the influent distribution pipes. So it will be entering in the reactor at different ports, and you will be having a anaerobic sludge blanket. That means a thick flocculent sludge blanket will be available in the reactor. So the wastewater will be coming here and it will be entering in the anaerobic sludge blanket through the influent distribution pipes. So what will happen? The wastewater will be passing through this anaerobic sludge blanket. So definitely this anaerobic sludge blanket is nothing but active microorganisms. So this active microorganisms will be coming in contact with the organic matter present in the wastewater. So what will happen? As a result, biodegradation will be taking place and more new cells will be generated, and as a byproduct carbon dioxide and methane gas will be produced. So everything will be moving together. That means gas, liquid as well as the solids will be moving in the upward direction like this. So this is the digestion zone of the reactor, and afterwards what we can see here, a transition zone is there. So here we can see this one, this is nothing but a deflector beam, and we have another arrangement like this. So all these things together, it is known as GLSS, that means gas, liquid, solid separation system. Here, because I have already mentioned here all the three components, that means the liquid, the biomass as well as the biogas will be coming up in this direction, and we want to separate all the components separately. That means we want to have liquid separately, we want to have solid separately, and we want to have gas separately. So that is what is taking place in this zone. So what will happen? The biosolids or the microorganism, it will be in the flocculant form, and the biogas whatever is produced, that also will be sticking to the microbial flocks. So as such the density of the flock will be less, so everything will be rising up along with the liquid, because this liquid will be having an upflow velocity. So with the same velocity or almost the same velocity, everything will be rising up. So once it comes here, okay, if it hits like here, what will happen? Okay, the gas whatever is present in the flocks, okay, microbial flock, it will be getting separated from the flock. So once the gas bubble gets separated from the flock, in the apparent specific gravity or apparent density of the microbial, that flock will be increasing. So definitely the settling velocity will be increasing. So the microbial mass will be going out like this, and whatever is the gas bubbles release, it will be coming and getting collected here. And as we see, okay, it will be some portion of the liquid and some microorganism or some flocks which is not yet removed from the system will be coming out through this portion. So we can see here the cross sectional area of this portion is very less compared to this portion. So what will happen to the velocity of the liquid coming out through this portion? The velocity will be gradually decreasing as the cross sectional area is increasing. So because of the velocity gradient and due to the settling velocity, the flocks, the microbial flocks will be getting settled here, and only clear liquid will be going up. So whatever the settled sludge whichever is present here, because we can see that this is an inclined plane. So because of the self weight, whatever the sludge collected here, everything will be coming back to the system, and all the sludge will be getting collected here. So we are getting clear effluent from this portion, and all the microbial mass whatever has escaped through this portion also will be coming back to the digestion zone, and we will be getting the clean or the biogas through this portion. So this system along with the deflector and the phase separator element is able to separate the gas, the liquid and the solids and retain a high microbial concentration in the system. So this is a typical UASB reactor, and it is having three zones. One is the settling zone, another one is the digestion zone, and third one is the transition zone. And if you want to see the efficiency of the system, here also we can use some empirical formula to get the efficiency of the system. The empirical formula usually used is E is equal to 1 minus 0.68 HRT raised to minus 0.68. Here also the HRT is in hours. So if you want to compare the performance of all these high rate reactors whatever we have discussed so far, we can see that this is the retention time, it is given in hours, and this is the COD removal efficiency, and this is the fluidized or expanded bed reactor. So we can see that even at very low retention time, the fluidized bed reactor is able to provide a high efficiency. okay, for a temperature greater than 20 degrees centigrade, because temperature is very important in anaerobic process. As the temperature decreases, the efficiency reduces drastically, and this is the performance of a UASP reactor. Up to 5 hours, 6 hours retention time, the efficiency is relatively lower compared to fluidized or expanded bed reactors, but for high retention time, say 10 hours, the efficiency of fluidized and expanded bed reactors and UASP reactors are almost the same. And this is the performance of anaerobic filter, we can see this one, and this is the efficiency of anaerobic pond, and compared to all these things, the efficiency of anaerobic pond is much less, because here what is happening, we do not have any mechanism by which we can maintain the microbial concentration in the system, or in anaerobic pond the hydraulic retention time and BSRT are not clearly distinguished, or we are not providing very high BSRT compared to hydraulic retention time in anaerobic pond. That is why the efficiency or the COD removal efficiency of this anaerobic pond is much lower compared to all these high rate reactors. So, the more microorganism we can retain in the system, the more the efficiency will be. And nowadays, because we have seen that in UASP or upflow anaerobic sludge blanket reactor, the reactor which is most commonly used for the domestic wastewater treatment in tropical countries, okay, there the sludge is in flocculant form. So, what will happen when the sludge is in flocculant form, its settling velocity is very low. So, if you give a high upflow velocity of the influent or the wastewater, what will happen, or your sludge will be rising up, and since the upflow velocity is very large compared to the settling velocity of the sludge will be escaping. Though you provide a proper settling chamber inside the system, we may not be able to capture all the microbial cells whatever is escaping from the system, and it will be difficult to maintain a high concentration of biomass in the system. So, in UASP reactors or whenever we use flocculant sludge, the upflow velocity is limited. We can go maximum of 1 meter per hour. That means, okay, if you provide more than that, the settling velocity of the sludge will be very less compared to the upflow velocity, and it will be washing away from the system. So, in order to avoid this problem, okay, because the limited upflow velocity, if you want to give a high organic loading rate or high volumetric loading rate, okay, we have to have a provision for changing the upflow velocity. So, as a modification of this UASP reactor, nowadays EGSP reactors are in use. EGSP reactor, what we are using, instead of flocculant sludge, we are using granular sludge. The sludge themselves, without the help of any inert material, the sludge themselves will be forming a granule of 3 to 5 mm, and definitely the granular will be having a very high settling velocity compared to the flocculant sludge. So, because of this high settling velocity, we can use a high upflow velocity, or even the wastewater enters in the system with a high upflow velocity, the sludge will be remaining in the system. So, that is the modification of UASP reactor. It is known as EGSP reactor, expanded granular sludge bed reactor. Another one is upflow anaerobic sludge blanket. It is a sludge blanket, here it is a granular sludge bed reactor. And as I have already mentioned, the granular sludge, the diameter varies from 1 to 5 mm, and it is having high density, and it is having excellent mechanical strength, high settling velocity, and high specific methanogenic activity, because the sludge or the granule will be having different types of microorganisms staying together. So, definitely the gas liquid contact will be very high. So, it always show a high specific methanogenic activity, and there are some disadvantages for this system. In EGSP reactor, inadequate for the removal of particulate organic matter due to the high upflow liquid velocity. Okay. This EGSP reactor is very good for the treatment of wastewater having dissolved organic matter, but if suspended organic matter is there, the treatment efficiency will not be very high. The reason is the organic matter whatever is present in the wastewater will be having a very low density. The density will be in the range of 1.05, 1.01 to 1.05, in that range. So what will happen if you have a very high upflow velocity? It will be going along with the liquid, the wastewater whatever we are giving to the system. So it will not be having enough contact with the microorganism whatever is present in the system. So the suspended solids will not be getting removed from the system, or the suspended solids will not be biodegrading in the system, because it will be washing away. Because we know that if suspended particles are present in the system, first hydrolysis has to be taken place, then only the organic matter will be available for the microorganism. As suspended form, it will not be able to penetrate through the cells of the microorganism. Unless it enters in the cells of the microorganism, microbial cells will not be able to metabolize them and convert it into biogas. So that is a major disadvantage of EGSP reactor. Now we will see another modification, that is two-stage anaerobic digestion. As we have already discussed, if suspended solids are there, EGSP reactor will not be able to do a good job. So if we can separate the hydrolysis step and the methanogenic step, okay, the reactor volume can be reduced considerably. So in two-stage anaerobic digestion, what is happening is, the first stage is used for hydrolysis and the second stage is used for methanogenesis. So in the first stage, all the suspended matter will be hydrolyzed and getting converted to soluble acids, and the pH of the system will be coming down, because most of the time the hydrolysis process is very fast and the reproduction time of this acid formers or hydrolytic and acid forming microorganisms are less compared to the methanogens. The sludge production also will be high, so the activity will be more. So we have to give only a low hydraulic retention time. Once the hydrolysis is taken place here, the hydrolyzed portion can go to a second stage where the methanogenesis will take place. So this is a schematic of a two-stage reactor. So influent is coming here. This is the hydrolytic reactor, and whatever is the soluble organic matter after the hydrolysis coming out, it is coming here and it will go to the methanogenic reactor. And methanogenic reactor, here we can use EGSP reactor, because we have seen that EGSP reactors are very efficient to treat wastewater having high dissolved organic matter. So here what is happening in hydrolytic reactor, all the suspended particles are getting converted to dissolved organic matter, and that is going to the EGSP reactor, and we will be getting the digested fraction here, and we get the effluent here. Now we will see the design criteria for USP reactor, because this is the one which is most commonly used in wastewater treatment, domestic wastewater treatment. So we will see the design aspect of USP reactor in detail. So first we will see the reactor shape and size. For relatively low strength wastewater like sewage, hydraulic loading is more important than organic loading. Okay, whenever we talk about the design of USP reactor, that too low strength wastewater like sewage, the hydraulic loading is more important than the organic loading, because this organic loading will not be the rate limiting step. The hydraulic loading will be the one, because if you provide a large hydraulic loading corresponding to the required organic loading, what will happen? You will be ending up with a high upflow velocity. So if the upflow velocity is more than 1 meter per hour, what will happen? The sludge blanket, whatever is present in the reactor, will be rising up and it will be washing out from the reactor. So that will be drastically reducing the efficiency of the system. So that is why I told hydraulic loading is more important for low strength wastewater compared to organic loading. Now if you want to decide the size and shape of the reactor, the USP reactor is having basically two important zones. We have seen three zones, one is the digestion zone, another one is the settling zone, and there is a transition zone also. So if you take the digestion zone and settling zone as the important things, it is advisable to provide equal area for both. That means 50% of the reactor will be used as digestion zone and the remaining 50% will be used as the settling zone. and usually the hydraulic loading rate 6 hours of HRT is sufficient in tropical and subtropical conditions to achieve a satisfactory removal efficiency. But if the temperature is low, if it is in the range of 10 to 12 degrees centigrade, we have to provide an HRT of 12 to 14 hours to achieve the same efficiency, because we have seen that for every 10 degree rise in temperature or fall in temperature, the efficiency will be decreasing drastically, because in tropical countries the temperature will be always above 25 degrees centigrade. So that is the optimum temperature for anaerobic process is 35 plus or minus 2 degrees centigrade. So at optimum temperature, the hydraulic retention time required for achieving the desired efficiency is only 6 hours, but if the temperature is less, then we have to provide a high hydraulic retention time. And if we want to find out the volume of the reactor, we know what is the flow rate of the wastewater Q, and if we multiply the flow rate with the hydraulic retention time, we will be getting the reactor volume, and this is the commonly practiced rule. If volume is greater than 1000 meter cube, go for multiple units. If the volume is less than 1000, we can go for a single unit. Now coming to the height of the reactor, we have seen how to find out the volume. The volume is decided based upon the hydraulic retention time and the flow rate of the wastewater. Now we want to see what is the height we can provide. The liquid upflow velocity decides the height, because we have seen that this is the limiting factor of a UASB reactor, and we can find out what is the VI. This is VI is nothing but the liquid upflow velocity, that is equal to QI by area of cross section. QI is the flow rate, influent flow rate, and A is the cross sectional area. So this is nothing but Q is the volume of the reactor by hydraulic retention time. So that will give you Q value, because volume is nothing but Q into HRT. So volume by HRT will give you Q. So Q by A gives us the velocity. So if you use like this, we can see that the upflow velocity is nothing but H by HRT. The area of this one and this one will be getting cancelled, and we will be getting upflow velocity is nothing but height by the hydraulic retention time. And we also know that this upflow velocity should not exceed 1 meter per hour in anaerobic system in UASB reactor, because the flocculent sludge will be having a very less settling velocity. So if the settling velocity is less than the upflow velocity, what will happen? The sludge washout will be taking place. So this is the limit usually provided. So for an HRT of 6 hours, the height should not exceed 6 meters. So the maximum height for the digestion zone in a UASB reactor you can provide is 6 meters. And one more reason is there, if you give more height, what will happen? The hydrostatic pressure in the reactor will be more. So naturally the CO2 solubility increases with depth. So if CO2 solubility increases, once CO2 get dissolved in the water, we will be getting carbonic acid. This carbonic acid will be reducing the system pH. So in this aspect also, it is not advisable to go for a very high reactor. Now coming to the shape, we can provide rectangular as well as circular. If you go for a rectangular reactor, it is having less structural stability, but a circular reactor, it is having high structural stability, but construction is difficult. And nowadays people are going for even hybrid reactors. That means the bottom portion is circular and the top portion is rectangular, or vice versa. The bottom portion is rectangular and the top portion is circular. So these are the geometrical shapes of few UASB reactor. This is a circular reactor. You can see this is the reactor zone and settling zone, and this is the gas collection system. And this shows a rectangular reactor, and this is a hybrid one. That means the bottom portion is circular and the top settler portion is rectangular. Now we will see how to go around for the design of phase separator. This is the most important component of a UASB reactor. Gas, liquid, solid separator. Its functions are, it collects the biogas escaping from the liquid phase. So that is the gas separation. And second one, it allows the settling of suspended solids. and it also helps to keep the effluent total suspended solids concentration low. And the last one is it creates a space above the separator for the sludge bed to accommodate expansion due to high temperature and high hydraulic loading. So, whatever is the excess loading coming to the system, so the reactor will be able to take care because it is having huge area above the solid liquid separator. So, how to design a solid liquid separator? So, this is the details of a solid liquid separator. So, we can see that here a deflector beam is there and here the separator element is there, and this is the interface between gas, the biogas and the liquid, and this is the settler. This is the settler. So, usual dimensions we can give deflector beam around 850 mm, and here this portion is 640 mm, and this is the separator element. It can have a width of 1360, and this portion, okay, this portion is 1150, or in other words, the overlapping between the reflector beam and the separator element should be at least 100 millimeters. That means at least 10 centimeter overlap should be there. And what is happening? The water, the wastewater, solids as well as the gas will be coming here, and here there is a reduction in the cross sectional area, and this separator element is placed at an angle of 45 degree. So, the water will be entering here at a velocity Vm, and this Vm is almost equal to 0.31 of V1, that means upflow velocity, and we can see that the cross sectional area is keep on increasing as we go up. So, here the VDI will be equal to Vi. So, what is happening here? We will be having a high velocity and it will be gradually decreasing. So, a velocity gradient is available. So, flocculation can occur, and this will be acting as a sedimentation zone also. So, all the biomass will be getting settled here, and this is having an angle of inclination of 45. Because of this, because of the self weight of the sludge, whatever is settled here, everything will be coming back to the reactor. And this GLSS, there are two possibilities to create a GL interface. One is with a submerged separator, and another one a separator situated above the water surface. If the separator is situated above the water surface, we have easy accessibility, but most of the time we go for submerged separator. Okay, this is a separator with atmospheric pressure, okay, because it is exposed to the atmosphere. Here we have easy accessibility, and this is a hybrid one, and this is a submerged one. So, we will see what are the advantages of a submerged separator. Definitely the corrosion will be high, this is a disadvantage, but the entire reactor area is available for solid settling. The biogas will be released under an high pressure and external seal to provide explosion during flaring. So, these are the advantages of submerged separator. So, it is better to have a submerged separator if you can take care of the corrosion. So, these are the velocities. If you want to find out the velocities, whatever is coming in the aperture, and this is the discharge velocity AVP, VAP, that is nothing but the upflow velocity of the liquid at the base of the GLS separator. That we can find out, we know what is the Q and what is the cross sectional area, then we can find out that velocity, and VDI, which is the upflow velocity of the liquid at the effluent discharge level, that also we can find out if you know the area at the discharge level. So, instead of providing the GLS as a single row, we can even provide under as different rows, so that okay, the efficiency will be much more. So, if you want to see the principles of design of a GLSS, okay, this one is very important. This portion we will discuss in detail in the next class, because we have to see how the influent arrangement, the effluent arrangement, and how to provide the inclination and all other dimensions of a GLSS. This portion we will discuss in the next class. So, we will summarize what we have seen today. We have seen what are the conventional anaerobic reactors which were used the earlier days. Those were the septic tanks and IMOF tanks. These septic tanks and IMOF tanks are being used nowadays also especially in rural areas. And here in this type of conventional systems, the biomass retention was very less, or we need a very high hydraulic retention time. So the efficiency was very less, or the volume of the reactor required was very less. So the anaerobic volume of the reactor required was very high. So anaerobic technology was not becoming very popular. So nowadays the hybrid reactors are available, which can retain a high biomass concentration in the system. The examples of hybrid reactors which are most commonly used nowadays for the treatment of domestic as well as industrial wastewater are anaerobic filters, downflow stationary bed anaerobic filters, fluidized bed reactors, expanded bed reactors, upflow anaerobic sludge blanket reactors, upflow granular sludge bed reactors. All these reactors are being used commonly nowadays for the treatment of domestic wastewater.